Ladies and gentlemen, I'm the presenter of Group 5. Today, I'm going to present about flow from the tank, pressure driven. These are my group members, and this is the question that I need to present to you. Suppose that we have a large tank attached with a nozzle. The tank is filled with compressed air in 3 kPa, and the nozzle is in diameter of 0.03 meters, while the end of nozzle is 0.01 meter. We are required to find the flow rate and the pressure in the hose, which is here, position number 2. Now, the main assumption of this chapter is that the flow is steady, inviscid, and incompressible. Because of this assumption, we can use Bernoulli equation along the streamline at 3 different positions. So, to find the flow rate, step 1 is to find the velocity of fluid in position number 3. We use the Bernoulli equation to compare the position 1 and 3. Since the streamline is horizontal, so there's no elevation, which means that Z1 is equal to Z3. At position 1 is a large tank, so we assume it is a negligible velocity, V1 equals to 0. Finally, since the end of the nozzle is exposed to the atmosphere, so the gauge pressure at position number 3 is 0. So, by substituting this information into Bernoulli's equation and rearrange it, we have this. Now, from the formula, we need to find the density of air. So, step 2 is to find the density of air using the ideal gas law. The question provided the atmospheric condition is in standard temperature and pressure. So, based on these two sources, at standard temperature and pressure, the information are these. Note that the ideal gas law requires absolute temperature and absolute pressure. So, every calculation involving absolute pressure and temperature. So, after calculating, we get the density of 1.26 kilo per meter cube. Next, substitute the information into V3, but note that this time the P1 is in gauge pressure, not absolute pressure, because of the context of Bernoulli equation uses gauge pressure. Then, calculate the flow rate using this formula. Since the cross-sectional area is pi r squared, right? And the R is D over 2. So plug it in, so we have this formula. After calculation, we get the flow rate is 0.00542 meter cube per second. Next, we need to find the pressure in the hose, which is the position 2. Now, because of the conservation of mass, the rate of flow in at position 2 equals to the rate of flow out at position 3. So we have this formula. So rearrange it, we get V2 formula. Then substitute the information provided, we get velocity at position 2 is 7.67 meter per second. Lastly, we use the Bernoulli equation again. Now compare position 1 and 2. We have the formula for the pressure in the hose again. Since we know the value of V2 already, substitute whatever inside the formula, we get 2,963 Pascal. So this means that the pressure at position 2 is 2.963 kilopascal. And that's it. These are the references, and that's all for my presentation. Thank you.